on gamma by left multiplication, then it induces an action of gamma on L2 of this. So maybe I should say gamma acts on this set also, gamma cross 1 through n. And but this set here is a basis, is a Hilbert basis of this Hilbert space. So in a sense that any other L2 summable function can be represented as a sum whose coefficients are L2 summable, sum of the basic functions. Basic functions are they correspond to elements of this set. Those delta, you remember delta sub x, where x is an element of this set. So this action on the basis gives an action of gamma on L2 of this set. And of course that's the same thing as, again, L2 of gamma n. So we have an action, and this is an example of what is called a Hilbert module. A Hilbert module, it's a Hilbert space together with a group action, essentially, and that group action is supposed to be preserve the norm. So it's in other words, it's a unitary representation of a group gamma in a Hilbert space. So gamma preserves the norm. The L2 norm. The action preserves the L2 norm. So this is an example of, so L2 gamma n is a Hilbert gamma module. That's just an example. I didn't give a general definition. A more general definition would be, so more generally, one can consider any subspace, any gamma invariant subspace. Let's call it V in L2 gamma n. Assume that it's gamma invariant. So I didn't say closed, and actually, so if this V happens to be closed, then it also becomes a Hilbert space. So a Hilbert space, by definition, it should be complete. If V is not complete, it's a subspace, but it might not be complete. You take the closure of V, that closure is complete here. Or alternatively, you could just allow a space to be non-closed. That's also an option. But in the definition, so there is a notion of dimension for such modules, and there are various definitions for dimension. Some definitions require the module to be closed. Some of them don't. So it's not really important that it is closed. But if it's a gamma invariant subspace, we can also call it a module. It's not going to be a Hilbert module because it's not closed. Hilbert space should be complete. But we can still call it a gamma module because the gamma acts on the subspace. Gamma is, because the subspace is required to be in gamma invariant. So if V is closed, then this is our definition. Then V is again a Hilbert gamma module. Hilbert gamma module. And for all our purposes, pretty much, this can be taken as the definition of a Hilbert module. So instead of giving a general abstract definition, one could say, okay, just take L2 of gamma to the power n and take any gamma invariant and closed subspace in it. This is our definition of a Hilbert gamma module. And then, yeah.
So it will be a set only finite.
We don't have to, yeah. What I'm saying is that for the purposes that for what I needed for this course, we can assume always that this is a finite. This is a finite number n. More generally, yes, you could take infinite powers here.
So, for example, we says something different with your definition.
Sorry?
With RU.
Say it again.
Wolfgang Greek. The two powers Wolfgang Greek in German. I think he has a book on article.
I'm referring his book. Yeah.
So what's
That's the name of the book.
what's the question?
I think L2.
So your definition is a little different from Lux's definition. That's what
I mean, there are several equivalent definitions. Yeah. So I wanted to give a basic example first, and then yes, there is a more general notion of dimension due to Luke, which applies not only in this situation but for generally modules over the von Neumann algebra of the group. So there is a formal definition, but for all intents and purposes for our course, this is enough. So we can consider just closed subspaces in this finite sum of L2 of gamma. So what's the dimension? The dimension. Let's consider an example. A very basic example. So consider the plane R2, and think of this being a Hilbert space. So for any two, think of elements being vectors in here, and for any two vectors, you have the dot product. R2 or complex numbers, let's say squared. And in R2, but let's take R2, so that I can draw the picture. So take a one-dimensional subspace and call it V. This is 0, and then you pick two vectors. Say, let me draw it this way, like this. I pick an orthonormal basis in R2. B1, B2, orthonormal, so two orthogonal vectors of length 1 each. And then you do the following. You take B1, and then you consider the projection of B1 into V. The projection of B1. So on the picture, that would be this vector here. The vector projected into V. The same thing for B2. This is the projection. This is the projection. And you take this sum, take this product, inner product, and do the same thing for B2. B2, the projection of V, B2. The question is, what is it? This is the dot product of two vectors. What's the dot product of B1 and the projection? It's the same thing as the dot product of the projection with itself. But the dot product of the projection with itself is the square of the length. So that's the same thing as B1 product with itself. Maybe I can just write down. So product with itself, that's the same thing as the length of this squared, plus the same thing for B2. The projection B2 squared. And now you need to compute this number. It's the square of this length plus the square of this length. What's the answer? The answer is 1 by the theorem of Pythagoras. Right, this length is the same thing as this length here. So you have the right-angled triangle. The sum of squares is equal to the length of this vector, which is 1. But this 1 happens to be also, this is the dimension over real numbers of V. I took V to be the one-dimensional vector space, right? This is an example of a more general fact. If I consider Rm, say, as a subspace of Rn, we can play the same trick. We could pick an orthonormal basis in Rn, and then each of those vectors we can project into this subspace. This is Rm, maybe I should say, let's call it V. V, which is isomorphic to Rm. it doesn't have to be the canonical copy, just any m-dimensional subspace in here. We could play the same game, right? Pick an orthonormal basis here, project every vector into this space, and then take the square of the length of each, and then take the sum. The sum, again, will be the same as the dimension, the usual dimension of the vector space over real numbers. So that shows, that gives a hint how you might try to define the dimension of this vector space. If V is a Hilbert module, Hilbert submodule of L2 of gamma n, so pick the standard basis. Basis, but now basis in what sense? What was the standard basis for this? The standard basis is this. It's the set of pairs gamma cross some finite set. But now the trick is when you consider the group action on this, we forget about the group. In other words, for each, like gamma cross 1, for each copy of gamma, so there are several copies of gamma here. For each copy of gamma, you pick just one basis vector corresponding to the identity element of gamma. Standard. So when I say the standard basis, it means basis as a gamma module. So in each orbit of gamma, you pick just one element. Gamma basis. B1 up to Bn. So in other words, B1, so like Bi is equal to, it's the delta function at the identity of gamma. This is identity. In the ith copy of L2 of gamma. So there are n copies here. For each copy of L2 of gamma here, you pick just the identity, the delta function at the identity element, and this is what we call Bi. And then the dimension over gamma now of V is defined to be the sum, I goes from 1 to n, of the same expression. So it's Bi and then the projection onto V of Bi. This is also known as the von Neumann trace of the projection. Goes Bi, the projection Bi squared. What's important is that this number actually turns out to depend only on V. So there is a choice involved, right? We chose Bi is here, the standard basis. We could take some other, we could make just an isometry of this space with itself and translate this basis into a different basis of the same space. That different basis, all these expressions will be different, right? This will be a different Bi you projected to this space. You will get a different number, but it turns out that the sum of these numbers will be still the same. So that's I will skip for now. If I will have time, then I might say some words. But it turns out that this number is independent of the choice of B1, Bn. As long as we pick some standard basis, some orthonormal basis, and pick just one representative in each gamma orbit, then you will get the same number. Why is this interesting or important? Because this kind of spaces, they occur quite often, kind of occur in nature. And one natural way to to find those spaces is to consider group actions on complexes. So if say y hat is a complex, is a cell complex, and gamma acts on y hat, there is an action, free action, freely, and again, I could assume in general, but we could also restrict our attention just to the case when this action is co-compact, freely and co-compactly. For example, you might say, take the Cayley graph of some group and consider the group acting on the Cayley graph. That would be an example. Then sigma I. If you have questions, you can ask.
What does delta 1 mean?
Delta 1, it's I defined it last time. Delta 1 is the function on the group, from the group to complex numbers, which takes value 1 on the identity element, and which takes value 0 on all other elements. So I gave a definition last time. So it's delta supported on the identity element of the group.
Is it very trivial that projection is well defined?
Yeah, I should have said, yeah. It's a standard fact from Hilbert spaces, right? A projection is well defined when the space is closed. I guess it's not completely obvious, but I will just leave it as a... there is a unique, so if you have some space and a subspace in it, and pick any vector, then there is a vector here with the property that there is a vector within this space, so let's call this V. There is a vector within this space, such that if you take the difference of those, that difference will be orthogonal to the subspace. So there is a unique such a vector in a space, and that is called the projection of this vector into V. So let's denote, okay. So let's denote sigma I to be the set of I cells. Sigma I of yeah, maybe I should say of y hat. Sigma I of y hat, it's the set of I-dimensional cells in y hat. So again, think about graphs, for example. If y hat is a graph, gamma acts on a graph, sigma 1 of y hat would be the set of all edges, for example. But then denote Ci2 of y hat. This is the space of L2 summable chains. So it's a generalization of chains that you have seen in like in algebraic topology class. So if you remember the definition of homology, for example, if you have a cell complex, what's the homology? You consider all I-dimensional cells in a cell complex, and then you consider all possible functions from that set of I-dimensional cells, two coefficients, say complex numbers. And you require those functions to be what? Or instead of a function, you think of linear combinations, right? A chain is a linear combination of I-dimensional cells. And since it's a linear combination, we require that there are only finitely many terms in that linear combination. So when I said functions from I-dimensional cells to complex numbers, say, I require that that function has finite support. So there are only finitely non-zero, only finitely many cells on which the function is non-zero. So linear combinations correspond to functions like this. It's a one-to-one correspondence. It's an equivalent way of describing chains. Now, instead of those chains, we consider a more general notion. We allow not just functions that are supported on finitely many cells, but we allow kind of functions supported on the whole set. Or in other words, we allow infinite linear combinations. But with the condition that this 2 stands for L2. we require that this is L2 of sigma I of y hat. So this means it's the set of all functions from the set of I-dimensional cells to the coefficients C. And as in the case of the usual homology, consider the space corresponding to I and consider the space corresponding to I minus 1. There is a boundary map from one to the other. And I might call this Ci of y hat. This is a subspace in it. And by this I mean it's the set of all chains. Usual chains, finitely supported functions on. So that's the same thing. Maybe we should call it C of this set, Ci y hat. These are all finite linear combinations of I-dimensional cells. So in other words, these are chains with coefficients in C. This is just a notation for it. But this is, by definition, this is what it means. And since it's a finite dimensional, finitely supported, an element here is a finitely supported function, then in particular any finitely supported function would be L2 summable. So all such functions are included here. And how do we define the usual homology? We consider the boundary map Ci of y hat to Ci minus 1 y hat. Take the boundary. So what's the boundary? You need to run the definition. Say if I is equal to 1, for example, then what's the boundary? You take an element here, it's a linear combination of edges. So you need to define a function just on edges. You pick one edge here, call it sigma, and then you associate to every sigma, to every edge you associate what? The difference of the vertices. We assume that there is an orientation on the edge, so we take sigma. This is called sigma, say sigma plus and sigma minus. Then you take sigma plus minus sigma minus. The difference of the two vertices of this. This defines a map, this boundary map. The boundary map maps edges to differences like this. And then if you have a linear combination of such edges, then you extend by linearity. There is a way to linearly extend to a linear map. Then you check that D is bounded with respect to the L2 norm. This is where we use this co-compact action. We use the fact that there are only finitely many orbits, gamma orbits in y hat for each dimension. So say there are only finitely many orbits of edges, there are only finitely many orbits of two-dimensional cells. And that means that what is this Ci y hat?
What do you mean by D is bounded?
So bounded as a linear, as an operator, as a map between vector spaces. So bounded means that what for any. So there is a number such that for any x in the domain Ci y hat, the L2 norm of the boundary is at most C times the L2 norm of x. L2 norm here, L2 norm here. This Ci, the trick is that what is Ci of y hat? This is L2 of, again, sigma I of y hat, I-dimensional cells. But what is this set? This is isomorphic to this is split into orbits. We have an action of the group. This set is disjoint union of gamma orbits. but each gamma orbit is a copy of the group because we assume that the action is free. So it's the same thing as gamma across some finite set. Finite set. Where this finite set is exactly the number of, like the cardinality of this set is the number of orbits. Let's say the cardinality is n. Then, or maybe that's the same thing as gamma to the power m for some m. So we have this boundary map. I wrote it only in dimension 1, but in higher dimensions one can do the same thing. If you have a two-dimensional cell, it's a two-dimensional disk. You look at the boundary of this disk, and you see how this boundary, how this two-dimensional disk is glued to the one-dimensional skeleton. You go along the boundary and see what kind of path it traverses in the one skeleton. And that gives you a linear combination of one-dimensional cells, of edges. So similarly, one can define it from dimension 2 to dimension 1, and so on. So you do the same thing for all dimensions.
By the way, don't we use superscript 2? No, in the next page.
See, oh yeah, sorry, yeah. I mean 2 here, yeah. So there is the usual boundary map. And what I want to say is that the same boundary map can be considered on this. So this boundary map extends to CI2 extends to a bounded operator, a bounded map. Since this was bounded, then you can extend it to bounded. So the formal construction is, you can note that this CI2 is a completion of this vector space with respect to the L2 norm. So there is a formal general construction. Or you could just do it directly without using any general theory. It's a bounded map, and then just as we define homology using maps like this, we can similarly define homology using these bigger spaces. So the l2 homology of y hat in dimension I is the notation is h2i of y hat, and the definition is you take the kernel of this map and then you divide by what? By the image of the previous map. That's the usual definition of homology. What we want here, we want the result still be a Hilbert space again in this situation. So the definition is slightly different. You take the kernel of di and you divide it by the closure of the image of di plus 1. This is d number I. Goes from dimension I to dimension I minus 1. So it's ci plus 1 to ci 2 to ci minus 1. We use this diagram. We take the kernel of this map and divide by the closure of the image of this. The image of a bounded map doesn't have to be closed in general. And why do we want to divide by the closure? Because we want the result to be a Hilbert space again. It is a standard fact. Then such a quotient, if you take a Hilbert space and a closed subspace in it, then the quotient has a natural Hilbert space structure. So say you have some big space and then you have a subspace V in it. What is the quotient? Say W is this bigger space and V is a subspace in it. What is the quotient of W by V? in the realm of Hilbert spaces, this can be identified with the orthogonal complement of V. So this is V. This is the same thing as the orthogonal complement of this space in this space. Yeah, and I should have said maybe that it's an exercise to check that the image of this map indeed lies in the kernel of this map, right? You prove it as in the definition of usual homology. So V in this case, it's the closure of the image, and W in this case is this kernel. It's the same thing as the orthogonal complement of V in W, this homology here. So this HI the homology can be viewed not just abstractly as in the usual definition of homology. In the case of l2-Homology, this is very explicitly a subspace in here, in the kernel. So in particular, so this lies in the kernel of the boundary I, and this is of course in the whole space of L2 summable chains Y hat. So you see the L2 homology actually can be viewed as a subspace, as a Hilbert subspace in the space of I-dimensional chains. And now the notion of dimension comes in. So what are the usual Betti numbers? For a cell complex. Complex, let's call it Y. So let's say finite cell complex. How do you define usual Betti numbers for a cell complex? You take the I-dimensional homology of Y with some coefficients. For example, again, I could take real numbers, for example, or complex numbers. Or integers. With integers it's a little bit trickier, so let's take, say, rationals or reals, or let's take some field. You take this homology, and then Bi by definition is the dimension of the I-dimensional homology of the complex. Say if you took it with complex coefficients, I should take the dimension over complex numbers. This is a vector space over complex numbers. These are the usual Betti numbers. Now we want to define an L2 version of these numbers. Maybe before I do this, let's do a little exercise. What is the, so if Y is a finite graph, what are the L2? What are the usual Betti numbers? So what is B naught of this Bi of Y? B naught and B1. B1 of Y. What's the answer? Is a finite. Let's see. How about we take it a tree? Say finite tree. That should be even a more specialized case, right? So Y is a finite tree. What is the zeroth Betti number? You need to define. You need to find what the zeroth homology is, and that is what? No, not quite. So take a finite tree, something like this. So what's the usual homology? The usual homology is the kernel of the boundary map. Right, C1 to C2, C0. C2 here is empty. I mean, it's the zero vector space. There is nothing there. So what's the first homology? The first homology is the same as the kernel of this map. What is the kernel of this map? Say if I take this vertex with plus and this vertex with minus, take this linear combination. What's the boundary?
Something not zero.
What?
Something not zero.
Yeah, see now. Yeah, I guess I'm thinking. Yeah, I'm thinking of the. Like with the complex. Just zero here, right? All I want to say is that what's the zero-dimensional homology first? Yeah.
So what is this homology?
They are all identified. So all those vertices become identified. They map to the same thing here. The zero.
So you have to take a quotient zero by image.
Yeah. Yeah, the image. So when you take the kernel of this map, which is the whole thing, by the image of this map, it is like identifying all possible vertices into one. So the dimension becomes just one. Each vertex will give you the same vector space. So the dimension, the zero-dimensional Betti number is 1. Okay, what's the first? That happens to be 0. So what's a good argument for that? What? Say it again.
We have no cycle.
We have no cycle. Yeah, we started with a tree. If there is a tree, then what you need to check that this map is injective. If it is a tree, but injectivity exactly means there are no cycles in a graph. So that's one way to see that the first Betti number is 0. Another way would be to know that homology is invariant under homotopy equivalence. And any tree is homotopy equivalent to a point. You can collapse the tree to a point. So the homology of a tree is the same thing as the homology of a point. But for a point, there are no one-dimensional cells anymore. So there is nothing. That's another way to see this. So just you see that the first Betti number of a tree is 0. Now we want to generalize this to this L2 setting. We also want to take a dimension, but the dimension we are going to take is this notion of dimension that I wrote. So the dimension over gamma is called the von Neumann dimension of V, dimension of a Hilbert gamma module. So in the same way, we can define L2 Betti numbers. So for a group action, for a free action by a group on some complex, and assuming it's compact, for example, define the L2 Betti number I, to be of this y hat with respect to the group action. So we have a gamma acting on a complex. This is by the definition is the dimension over gamma of the I-dimensional homology of y hat. So remember again that I-dimensional homology is a subspace in here. And if we have a group action on y hat, it is easy to see that the kernel of the boundary map will be invariant under the group. And the image also is going to be invariant under the group. So this kernel is a subspace in here. And it's not just a subspace, it's also closed. Kernel is always closed. So this is, and the subspace is invariant under the group. So this kernel is an example of a Hilbert gamma module. The closure of the image, the same thing. This image is invariant, so the closure is also going to be invariant under the group. When we took the quotient, that's equivalent to saying to taking the orthogonal complement within the kernel. But that lies in here. So the homology is also a Hilbert gamma module, gamma submodule of this gamma module. And since this is a Hilbert gamma submodule, we can define the dimension of that in the usual way, which is you pick some bases in here and then project bases in the ambient space. You pick some orthonormal bases and then project and take the sum of squares of the normals. So this is the ith L2 Betti number. L2 Betti number for the action of gamma on y hat. So let's consider an example. The first example is that take gamma to be just the trivial group, and consider gamma action on a complex y. Y is a complex. And this is the obvious action, right? Gamma consists just of one trivial element. For this action, what is the I-dimensional L2 Betti number for this particular action? Maybe let me call it y hat, but it's y hat for gamma. Gamma is the trivial group now. We follow the definition. We take the L2 homology is I guess I should say. How about we take a finite complex just to avoid any technicalities? Finite. Finite complex. So the trivial group acting on a finite complex. What's the I-dimensional homology? L2 homology of this. You follow the definition. You take the kernel and divide by the closure of the image. But this space here, what can we say about this space of chains? Say it again.
Same as without 2.
Because it's finite. The set of I-dimensional cells here is finite. So this is a finite dimensional vector space. In other words, we consider all L2 summable functions on a finite set. But that's the same thing as the set of all functions on a finite set. Just all finitely supported functions, right? It's the same thing. So in this case, this Ci, the kind of viewed as a Hilbert space, is the same thing as just a vector space generated by a finite set. Okay, then we take the kernel, divide by the closure of the image. The image is going to be a subspace of a finite dimensional vector space. It's always closed. And then take the quotient. It's a finite dimensional vector space. But you see, we take the dimension over gamma. What's the dimension over gamma? We need to recall that picture that I drew at the beginning, R2 and the subspace in it. Right. So instead of 2 here, you just have some finite number. The same thing. And now V, this V here is this homology. So what's the dimension? How did we define dimension? We consider the gamma action on a complex in dimension I, on all those I-dimensional cells. And in each orbit, we picked just one element, Bi. That basis we projected into the subspace. If you follow what we did, we pretty much now what are the orbits? If gamma is trivial, each orbit is just one choice of element. Each orbit consists of just one element. So picking an element is just picking the same thing as picking an orbit. So after you check all this, you see that the dimension over as a vector space over complex numbers is the same thing as this dimension over gamma, if gamma is the trivial group. So this is the same as the dimension over gamma of h2i of y hat. But this, since everything is finite, this is the same thing as the dimension over complex numbers of the usual homology y hat. But this is, of course, we have a name for it. This is b sub I of y hat. This is the usual Betti number in dimension I. So if the complex is finite and if the group is trivial, then we recover the usual Betti number. L2 Betti number is the same as the usual Betti number. Is it any different? Is the L2 homology any different from the usual homology? So consider another example. Let's take y hat to be this line subdivided into intervals. So it's a one-dimensional complex, a graph, which is an infinite line subdivided into intervals. And let's take gamma be the group of integers. So this gamma acts on y hat in the obvious way, right? What's the action? You pick some number and you want to define how this number acts on this line. The action is just, if you pick number 5, say, then you translate this line to the right by 5. So it's the translation action. Okay, the dimension of y hat is 1. So there are 0-dimensional cells and there are 1-dimensional cells. The question is, what are the L2 Betti numbers for this action? What is the homology and what are the L2 Betti numbers? Let's see. Let's follow the definition. C1, 2, y hat, then C0, 2, y hat. Then before, this is C2, but that is 0, because there are no two-dimensional cells. And then we have 0 here. So this is all. All the rest, you can extend this diagram by zeros infinitely. But the essential part is concentrated in dimension 0 and 1. So all L2 Betti numbers in dimensions other than 0 and 1 will be zeros. These two are only non-trivial cases. Okay, what are they? So we really need to investigate what this boundary map is. To each edge here, it associates the difference of the vertices of this edge. That's the boundary map. And what is H1? Since we are talking about a graph here, what is H1 of y hat? It's the kernel of this map divided by the closure of the image of this map. But the image of this map is 0. So the kernel, the homology, the quotient is the same thing as just the kernel of D1. Right? In order to find the first L2 Betti number, we need to find the dimension of this kernel. And what is, let's write H02 of y hat is. This is, by definition, the kernel of this map divided by the closure of the image. What's the kernel of this map? It's the whole space of L2 chains. It's C0 of y hat divided by the image of, by the closure of the image of D1. Okay, so what are they?
So you say gamma module T1 is 0.
Gamma module is
T1 is 0. 0.
what is 0? Sorry.
So image is 0.
Image of what?
T1.
Of C1?
T.
The image of this.
Yes.
So is it 0?
It is not good.
So good question. What's the map?
There's a gamma module, so they are same models.
So in the kernel, there is only constant zero constant function is the kernel, right? So that's the same.
The zero function is the kernel. By which you mean this map is injective?
No. So you think of this L2 thing as a, I mean, you can view these elements in the chain complex as either function or linear combination of these.
Either way, it's an equivalent.
Right?
Yeah.
As a function, because it has to have the same, it must be constant function, right?
What? The kernel?
Kernel, yeah.
The kernel, yeah, it must be constant. Yeah. So yeah.
Constant function
So
converges to zero constant function, right?
yeah. Yeah. So what's the kernel? Yeah, the kernel of D1. It consists. What's the kernel? It means that. So you have a. It's a linear. It's an infinite linear combination of edges. It consists of such linear combinations. So you put some number, whatever number, say a, on this edge, right? But since the kernel, so I'm reconstructing some chain which lies in the kernel here. If it lies in the kernel, the boundary of this chain must be 0. Then the question is, what's the value of that chain on this edge? Since the boundary map of this chain is 0, it means that the coefficient that comes from this edge and the coefficient that comes from this edge at this vertex, they should cancel out. They should become, the sum should become 0. But that means that since the edges are oriented, say orient edges like this, then it means that the value on this edge also must be a. But then the contribution of these two edges to this vertex should be, the total contribution should be 0. So the value of this chain on this edge also must be a, and so on. That implies that, yeah, this chain, so any chain in the kernel of D1 must be constant. Exactly. Yeah, and if it is a constant, then it must be the 0 constant, because if a is non-zero, then what's the L2 norm of all these? The L2 norm of these will be infinite. We don't allow this. We only consider L2 summable chains. So then it must be 0 constant. Constant 0. And that implies that what? It implies that, so any element in the kernel must be the 0 function. So it means that the kernel of D1 is 0. That maps that, that says that this map is injective. So D1 is injective. Okay, so that tells us something. This kernel D1 is 0. So that implies that the zeroth L2 beta number of y hat with respect to gamma, it's a gamma dimension of the 0 vector space. And that is 0. You can check this from the definition. Okay, so the 0th L2 beta number is 0.
Is it 0 or first?
Oh, sorry. What am I saying? Yeah. Sorry, the first one, yeah. But the 0th is also 0. So there is no mistake in this. I claim that the dimension of this space is 0 as well. How can one prove this? So there are two ways. You either argue directly somehow, you argue directly to check to show that the closure of the image is the same as the whole space. In other words, the closure of this map is dense in the space of zero-dimensional chains. Or you could argue by dimension. And so before we do this, let me mention this. It's a general notion. It's a general property of dimension. Dimension gamma is additive. By which we mean the following. So if 0, A, B, C is a short exact sequence, so what is a short exact sequence? It means I'm assuming that A, B, and C are Hilbert gamma modules. And I'm assuming that the maps are bounded maps. Bounded maps between like normed vector spaces.
So also gamma module.
Exactly. So these are not just bounded, but they should be in the category of gamma modules. So it means that this map should commute with the action. So there is a group action on this, group action on this, group action on this, the same group. So I assume that these maps commute with the group actions. And also, so what is a short exact sequence? Exact means that the image of this map is the same as the kernel of this. Image of this is the same as the kernel of this. And image of this is the same as the kernel of this. We can require a weaker condition. We can only require that this map is weakly exact, is a weakly exact, I say short exact sequence. By which I mean weak means that the image of this map is dense in the kernel of this. So in other words, the closure of the image of this map is the same as the kernel of this map. So up to closure, it's exact up to taking closures. Exact sequence of say Hilbert gamma modules. Then the dimension of gamma behaves in the same way as the dimension of finite dimensional vector spaces. So the dimension of the middle term is the same as the dimension of A plus the dimension of C. So this requires some proof. In general, it requires some work to establish this, but you might do it exercise. So if B happens to be A plus C, the orthogonal sum. So I'm taking some Hilbert gamma module A, Hilbert gamma module C, and then take the orthogonal sum of them. So it's the usual sum of vector spaces. And we put the inner product on A, it already exists, on C it already exists. And if you have two different vectors, one in A and one in C, then we declare them to be orthogonal. The orthogonal sum. Then the same holds. Then the dimension of B is the same as the dimension of gamma A plus the dimension over gamma C. I suggest that you prove this using the definition that I gave. The definition was what? We assume that there is some ambient space. All this is contained in some W, where W is an ambient space. And you can take this ambient space in this case to be what? To be this sum. And then you pick a basis for this W, and then you project that basis onto the onto A, onto C, and then on the into A, into C, and in the whole thing. And you can relate the two, right? Pretty much what you will use is the theorem of Pythagoras, right? The projection to A squared plus the projection of to C squared is the same as the projection to B squared. It's the Pythagoras theorem that you use in this case. So if it happens to be an orthogonal sum, that follows pretty much immediately from the definitions. And this is a more general statement. And the idea, there is a theorem in analysis, polar decomposition theorem. You use polar decomposition to reduce this general statement to this example. Okay, going back here. So there is a direct way to show that this quotient is 0. Or there is an indirect way. Let's do it both ways. So since we already know that the kernel of di, the kernel of d1 is 0. The kernel of this map is 0, so this is an injective map. So you can consider this. This becomes, I might extend it by 0 here. This part here. This is a short exact sequence. Short, weakly short exact sequence. Because, I mean, we want to show this, right? Maybe not. Yeah, this is not exact. Yeah, I should take a different one. C1, 2, y hat. Yeah, consider this boundary map. Yeah, C0, 2, y hat. And then here I don't put 0. I put the quotient. I put C2, 0, y hat, quotient by the closure of the image of d1. This is d1, right? This is now a weakly short exact sequence. I can complete it with 0 on the left and 0 on the right. This is now weakly exact. And what's the dimension of this? So the dimension over gamma of C1 to y hat. What's the explicit description of this space? It comes from this example here. We have a gamma action on this, on the set of edges in this graph. How many orbits does it have? How many gamma orbits of edges do we have? Just one orbit. So this space is actually isomorphic to dimension gamma. We have a copy of L2 of gamma for each orbit. But we have only one orbit in this case, so that's the same thing as L2 of gamma. Now you need to compute what the dimension of L2 of gamma is. Again, follow the definition that I gave. You pick a basis for gamma. It's the delta function at the identity. And then you project that function to this space. The projection would be what? That function already lies in this space. So the projection of that function into the space will be the same function. It's the function itself. And then you take the square of the length of it. It is 1. So the dimension is 1. The dimension of this is 1. And this map is injective, right? Yeah, we still need to. Yeah, you're right. I don't think I can use really the dimension argument here. Yeah. C0. The kernel is. Yeah, just dimension is not enough. Yeah, I really have to describe what it is. Yeah, I somehow thought that I could just get away with by formal argument. No, we really need to prove that this is 0, right? Then C0 of y. Ah, no, I can get away. What's the dimension of this one? The dimension of gamma of C naught L2 of y hat. What's the dimension of this space? Again, explicitly describe this space. We consider the orbits of vertices for this action. How many orbits do we have? Just one orbit of vertices. So this space, again, it's the same as L2 of gamma, which is of dimension 1. Okay, we have a weakly short exact sequence. The dimension of this is 1. The dimension of this is 1. And then, what does it tell you about the dimension of this space? It should be 0. So then, the dimension of this is 0. Okay, if we know that the dimension is 0, what does it tell you about the space? And that's another general statement that one can give. If V is a Hilbert gamma module, and the dimension of V over gamma is 0, then what? Then V is 0. Just as with finite dimensional vector spaces. How do you prove this? You use the definition that I gave at the beginning. If it's not, you argue by contradiction. If it's a non-zero vector space, remember we picked those B1, Bn. That was the basis for some ambient space. But then you consider all possible translates of these. All possible gamma translates. They give you a basis of the Hilbert space. So these vectors, together with all possible translates, give you a basis of the Hilbert space. And then you check that since V is invariant under the group, you use invariance. So you argue by contradiction. If V is non-zero, then there would be one of these vectors or one of those translates which would project in a non-trivial way here. And if that's the case, then the dimension would be non-zero. So it's an exercise in a definition of dimension and using the fact that V is invariant under gamma. So that's a nice property. So the dimension of this homology is 0. That implies that the homology itself is 0. Of y hat is 0. And that means that the 0th L2 Betti number is 0. That was kind of an indirect way of proving, but it's an illustration that you can often use additivity when you deal with L2 homology or with L2 numbers. Let's actually prove this directly. That's also a very good exercise. Let's show that the closure of the image is indeed the whole space of zero-dimensional chains. The second proof. We want to show that the image of D1, the closure of the image, is the same as the space of zero-dimensional chains. It means that any element, any L2 summable zero-dimensional chain can be approximated by images of L2 summable one-dimensional chains. But that's equivalent to saying that you can approximate every element in the basis of this. So you pick some basis in. You remember this is a copy of L2 of gamma, pretty much. If you can, and those delta x, those form the basis of this Hilbert space. So saying that this is dense, saying that the image is dense, is equivalent to saying that you can approximate every single delta function by images of one-dimensional chains. So let V be a vertex in y hat. So this V can be viewed as a delta function here. So we think of this. So V, you can think of this being an element of C0 to y hat, right? To each vertex, we can associate the delta function, which is 1 at this vertex and 0 everywhere else. So that's the identification between vertices and functions, L2 summable functions. There is an explicit way to approximate this particular V. So here is our graph y hat, and here is V. So I'm drawing a general picture, right? And what I'm assuming here is that this y hat is infinite. So it's a, if you like, let's assume that y hat is connected, and infinite. So I'm taking, and since we are working only in dimension 1 and 0, it could be a complex, for example, but we only consider the 0 dimension and 1 dimension. So we are essentially talking about graphs here. So take any complex or a graph which is connected and infinite. Since it's infinite, then for any n, for any n, pick a subset W into the set of edges, into the set of vertices, into sigma naught of y hat. So that's the same thing as what this is what we called V of y hat, the set of vertices in y hat. 0-dimensional cells are the same thing. Subset W sub n such that the number of elements is n. The cardinality of Wn is n. So this is where it is on the picture. This is Wn, and it has n vertices in it. Since y hat is connected, we can draw a path to each of those. To each of those vertices. Say, let's pick a vertex W here, and pick a path. So this path, let's call it P sub W. So for each W in this set, Wn. For each W in this set, you connect V to W by a path. Call this path P sub W. And then take the sum of those. You take V minus the sum, I goes from 1 to n, of the boundary of the path divided by, let's see, divided by n. Yeah, I'll put it straight. Yeah, maybe I should say P, yeah. P sub W, yeah. W is, that's what I wanted to say, in W. So it's a linear combination of all those paths, the uniform kind of distribution over those paths. So what's the boundary? And then I want to take the L2 norm of that. That's the L2 norm of the 0-dimensional chain. Let's see what this is. So it's V minus, what's the boundary of a path? It consists of edges, right? But for each edge we take the difference of two vertices. So those vertices that are inside, they will cancel out. The boundary of a path would be this W minus V, if we orient the path this way. Then it's the sum over all W minus V over N. The L2 norm That is what? You split this into two parts. You have W over N and take the sum. And also you have V over N, take the sum over all W. But V does not depend on W at all. It would be what? V minus this linear combination of V, which is again V itself. So V will cancel out. And what is left is the sum over all W, W over N, the L2 norm. So W runs through a finite set of cardinality N. And for each vertex in this, this is the coefficient. This W comes with the coefficient 1 over N. And now, so it's a uniform distribution it's a function that takes the same value, 1 over N, on a finite set of cardinality N. What's the L2 norm of that? So that's where the square root is going to be important. Right? It's the square root. Or actually, it's not really important, but I better write it. What's the L2 norm? It's 1 over N squared plus and so on, 1 over N squared. And how many times? N times. It's 1 over N squared and then multiply by N. That is 1 over N, and then we take the square root. What's important is that this goes to 0 as N approaches infinity. So if you pick this Wn bigger and bigger sets, you pick a sequence of Wn's sets are bigger and bigger, then what did we show? We show that for this given V, there is this sum, but this sum is a boundary. This sum here, it's the same as the boundary of paths divided by N. It's the boundary of something, of some one-dimensional chain. I'm thinking of a path being a one-dimensional chain, right? I think of this being a linear combination. So this is a boundary. This belongs to the image of what? Image of D1. And even more, those paths are actually just finite paths. So it lies actually in the image of this C1 of y hat. We only considered finite linear combinations of edges. But it certainly lies in the image of this whole map. So it's the image of D1. So for V, for each number N, we picked a boundary, and we showed that the difference between V and that boundary becomes smaller and smaller. So it means that we constructed a sequence of boundaries which approximate V. So this is a very explicit construction. All we used is the fact that y hat is connected and infinite. So this implies that the closure of the image of D1 is the whole space in here. This proves this equality. So it's a very explicit way of, and this is a good time to finish. Yeah. If you have questions, please ask them.
So gamma action is not important to calculate the homology, right? So gamma action is only used for calculating dimension.
Gamma action, yeah. For homology, you don't need gamma action. But to compute dimension, it really makes a difference.